Hi there. Thanks for joining us on a Q&A edition of Space Nuts. My name is Andrew Dunkley, and this is the show we do each week where you supply the agenda and we pretend we know what we're talking about. And questions are coming in for this week's show from Peter, who's asking about climate change. Paul is, well, I suppose it's a similar story, Snowball Earth. And a couple of objects of interest. Casey is asking about KM M3230213A. Know all about it. And an even more obscure thing, Henrik has asked about MWC349A, which I just did a Google search for, and it came up blank.
Anyway, it's an A at the end, not an A. I had fun with that.
Is that the one?
Yes.
All right. And that's what we're talking about with that little voice you just heard in the background on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And that voice belongs to none other than Professor Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. Jonti, hello again.
Good afternoon. Yeah, clearly Professor of Interruptions. This is what happens when I've had enough time for the coffee to kick in.
Yes, it's been, 4 days and we're still wearing the same clothes.
Absolutely.
Yeah, I get a lot of mileage out of that joke.
Oh.
Yeah.
But you've been and had a musical interlude, haven't you?
I have. Look, it was just last weekend was a long weekend in New South Wales, and I think it was in Queensland too. But it was the weekend that Taylor Swift released her latest album, and I've got 3 granddaughters, all of Taylor Swiftie age. And we took them to see the launch of her new album. I've got to tell you, I really did. Did I enjoy it? Yes. It's not aimed at me or my demographic, but it was interesting to watch some of the thinking behind the artist and some of the creativity that went into film clips and things like that. That's what I got out of it. But what an extraordinary
It's one of the things I love. I know we've gone totally off topic straight away, but my favourite film critic, and the kind of only one I pay attention to really, is a guy called Mark Kermode in the UK, who's they used to be on BBC Radio 5 Live, and now they've got their own independent thing. And it's one of those things that's like comfort food for the soul that you can listen to and just makes your children relax. But part of what's nice about him is that you get a lot of film critics who, if a film's not made for them, are instantly scabrous about it, right? And, you know, I remember this with the Twilight films, which I'm not the target audience. They're not my cup of tea, but they got panned because they're made for teenage girls and film critics are elderly men. Yeah. And there's a slightly different demographic there. Yeah. And this guy's brilliant because he'll make the point, you know, I'm not the target audience for this. I'm very clearly not it. And I enjoyed it okay, but you look around the room at the people who are the target audience and they love it, so it's obviously doing well. I think it's the same with what you're saying about the Taylor Swift stuff. We're not the target audience, but you can appreciate that this is someone who's awesomely talented. And for the target audience, it's really fundamentally awesome, you know.
Yeah. I was still working on radio when she was announced by Time magazine as Person of the Year. And I did a big, big statement at the time, as far as I was concerned, about why she deserved it, because she'd brought light into the world at a very dark time towards the end of COVID. And but then they went and made Donald Trump the Person of the Year. So anyway, whatever.
Can't see the light without having darkness, right?
And I will say one of the songs on the new album has got to be about Donald Trump. So anyway, he's after a Nobel Peace Prize, and the word on the hill is that he might just get it. We won't go there. It's not our agenda, but we will go to some questions. Why don't we try and tackle this very first one? And this one comes from Peter. With all this climate change happening, I was wondering how CO2 is warming the planet when it's heavier than air. Maybe the problem is the axis of the planet has moved because of all the millions of tons of minerals that have been moved. maybe someone should check the axis angle. Cheers, Peter. I think I've heard this theory once before. I doubt that the amount of stuff we take out of the ground and move around the planet is going to make that big a difference to the tilt.
No, and the beauty is we can measure the tilt. I mean, I grew up in the north of England, and high in the sky was Polaris, the pole star, which is the direction that the northern end of the Earth's spin axis points to. Very, very close to that star. So we can see exactly where the spin axis of the Earth is pointing. We can measure its spin rate. And it is right that moving material around on the Earth will, to some degree, change its spin and change its spin axis tilt. But, and it's a very big but, the amount of change that you get from human activity is very, 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 very small. A much bigger shift in mass, for example, happens with melting of the polar caps.
Yeah.
So if you melt the polar caps, you move the water settles all around the Earth, so you're effectively moving mass from near the poles to near the equator. And that changes the Earth's rotational angular momentum and will change the Earth's spin very, 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 very slightly. But we're now incredibly technologically capable, so we can measure things that are that small. And a good example of that was the big Indian Ocean tsunami, the earthquake that caused that on the Pacific Rim, had a measurable effect on the Earth's spin. But if I remember rightly, and I stand to be corrected here, that measurable effect was something like 1/1,000,000th of a second in the spin rate or something like that. And we can measure that, but it's not like you'd notice it in your day-to-day life. And it's not like that would be big enough to cause the impact on the climate that we see today. Now, I understand that thanks to decades of discussion that climate change is still a bit of a controversial topic with some people. And, you know, I'm quite fundamentally comfortable saying climate change is a real thing, that the climate is changing. I spent 3 years early in my career living in Switzerland. And when I was in Switzerland, I used to go skiing because skiing's awesome. And if you're in Switzerland, why wouldn't you? And all these beautiful little towns that I went to in the winter, and then you went back in the summer and you went walking in the hills instead of skiing because all the snow had gone. They all have these photos from 50 or 100 years ago where you had the village in the foreground and the glacier in the background winding out of the hills. And then if you're up there in the summer, you'd go out and look and it isn't there anymore because it's retreated that far. And I think that's fundamentally why in a lot of those countries with alpine regions, climate change has been accepted for much, much longer, because you can really physically see the effects. And so it's very clear that it's happening. And the argument that it's caused by humans rather than something natural, the strongest evidence for that, to be honest, is the speed at which it's happening is unprecedented. Yes. The natural effects that could cause it, like the transition from the ice ages to the interglacials, and we'll talk about this a bit more later on, are much more gradual. Changes in brightness of the sun are much more gradual, and in fact the sun has dimmed a little bit over the time that we've been measuring climate change due to little bits of tweaks in its behaviour. So if the climate wasn't changing, we'd actually be slightly cooler now than we were a couple of hundred years ago. Only very slightly. But that leads to this perverse and confusing statistic that 110% of all climate change is caused by humans. Because we're not just making it warmer, but we're offsetting the cooling as well.
Yeah.
So that's all the background to it here. How carbon dioxide plays a role, even though it's, you know, heavier than air, it's still gas, it still floats around up there. It's not like it all sits at ankle level on the Earth. But even if it did, it would still be fairly effective, because what carbon dioxide is, in a really broad sense, is it's like a good winter doona that you've got. The way that I can understand this as an astronomer most obviously is, I think back to, again, when I was a kid, 1983, when I was 5 years old, there was this satellite launch called the Infrared Astronomical Satellite, IRAS. And that was really foundational for a lot of what we've learned about planets around other stars, because it was a tool that first allowed us to find debris disks around stars, which are the leftovers from planet formation. And that was a bit of a shock, because stars didn't look how they were expected to, three of them in particular, Vega, Fomalhaut, and Beta Pictoris. They were brighter in the infrared wavelengths than we expected. They thought the satellite was broken, then they realized that, no, really, the stars just had all this debris around them that was getting hot, warming up, and giving off radiation in infrared wavelengths. So this tells us that when you heat something up, it radiates that energy away in infrared, and that's why thermal imaging cameras work. You know, you can see people at night if you're using a thermal imaging camera because they're warmer than the surrounding area, so they give off more infrared radiation. You can see them. But the reason we had to launch IRAS was that you can't do infrared astronomy from the ground except at a couple of very specific wavelengths. And the reason that you can't do infrared astronomy from the ground is that the atmosphere is fundamentally opaque at infrared wavelengths, and a big part of that is carbon dioxide. So if you've got a photon of infrared radiation, it coming into our atmosphere will essentially see our atmosphere as utterly thick cloud. It'll be absorbed and re-emitted back out. Optical light, visible light, makes it through the atmosphere intact. And that's why if I look out of the window at the minute, we've got a lovely sunny day and I can see what I'm doing. And that solar radiation comes in and it warms the Earth up. And what does the Earth do? It radiates that energy back outward at infrared wavelengths. But because the atmosphere is opaque at infrared wavelengths, that energy gets absorbed and re-emitted. And it'll be re-emitted randomly in any given direction. So the odds are it'll come back down. So in other words, that radiation gets trapped. And that's how the Duna works. That's how the carbon dioxide's working. Now, the carbon dioxide we've got in our atmosphere is really effective as a greenhouse gas. It's actually mostly saturated. So adding some carbon dioxide from no carbon dioxide would have a much bigger effect than adding carbon dioxide to the atmosphere now when we've got a fair bit of it in there already. But it's not totally saturated. So what that means is as we add more carbon dioxide, it can still have a bigger effect. And that's why as we put more carbon dioxide into the atmosphere, the Earth gets warmer because the Duna gets more effective. There are other gases that are effective greenhouse gases as well. Methane is a really good example. Methane is actually much more effective than carbon dioxide. But the difference is methane's fairly short-lived in the atmosphere. Methane molecules, on average, will be removed from the atmosphere within 400 years by interacting with oxygen. Carbon dioxide is only removed by life or by weathering. You know, if you get lots of rain on the continents, that breaks up the rocks crumble down, chemistry happens, carbon dioxide can be pulled out into the rocks and locked up in the surface. They're the mechanisms that get rid of carbon dioxide, and they're slower. So that's part of why carbon dioxide is a problem, because when we put it in the atmosphere, it's going to hang around for a good long time. Mm-hmm. But that hopefully kind of answers that question there. I am respectful of the fact that it's hard for people to comprehend how we can change the world's environment, because you think of yourself and your friends and you think the Earth's so big and we're so small, how can we have that much of an effect? And it's hard to come to terms with just how many people there are and just how much stuff we're doing and pumping stuff into the atmosphere. Yeah, it's a bit misleading to say, you know, if you change to an EV rather than a petrol car, you'll save the world, but you'll contribute a little drop in the ocean towards lessening climate change potentially in the long term. And that's kind of what people are looking at. But fundamentally, this is what's happening. It's very, very well established. Nothing astronomically can even come close to explaining what we're seeing. So when you rule out all the other options, the only thing that's left is human influence. And that's kind of sad, but shows what an effective species we are at changing our environment, you know.
Well, hopefully we can be just as effective in finding a solution, but I think to do that, everybody has to be on the same page, and that's just not the case at the moment.
I'm an optimist. I mean, there's...
so am I, but...
There's real challenges here. I remember there was an incredible article by a guy called Jeff Masters, who used to run the Weather Underground site. He used to write blogs there.
Yeah.
And he wrote about, I think it was a book review actually, but he wrote about something called manufactured doubt, which is a whole industry that has sprung up to sow confusion over something that should be settled science in order to allow business to operate without being restricted effectively. And it first came about with smoking. So cigarette smoking, tobacco smoking was known to be very harmful to people going back 100 years from now. But even when I was growing up in the 1980s, you still had smoking in public places. You still had it everywhere. You still had adverts on TV and tobacco sponsorship, because there'd been this very cleverly managed marketing strategy of casting doubt on the science and casting doubt on the scientists involved, effectively slandering them. And you had things like, you know, top sportsmen in the world, footballers and cricketers and things like this, being sponsored by tobacco companies and smoking cigarettes in interviews and giving this impression, can't be harmful, can it? I mean, look, here's one of the fittest athletes in the world and they smoke and that makes them a great athlete. You shouldn't teach children. And what was interesting in this article from Jeff Masters, who's a very powerful advocate for knowledge about climate change, was that there is a lot of evidence that the companies that used to do that for tobacco through the 1980s were brought on board by the big oil companies to do the same kind of strategy. And it's been incredibly effective. And I think it's led to this wider thing of diminishing trust in science and greater doubt in it, which has led to the challenges we face now with things like vaccines, with, you know, flat earthing to some degree, with places where people are skeptical and don't trust scientists and don't trust science, even though science is so fundamental and foundational for our day-to-day lives. And it's really sad. But the flip side is we got cigarettes banned. People's health has improved. No longer do you go to a pub and the walls are grimy and the windows are dark because of all the cigarette smoke. No longer do you get on a train and have to cough your way to your destination. Things have changed. And I think we're starting to see the same change with climate change and with the actions that we can take. And it's not happening out of the goodness of people's hearts. It's happening because commercially it's now becoming viable to make the changes.
Yes.
Like the electric vehicles are a really good example. Back in the early 1900s, you had electric vehicles. We had electric milk floats in the UK, but they were an oddity and they were specific use. But it's finally got to the point where those kind of vehicles can be competitive with combustion engine vehicles, can even possibly work out cheaper and more efficient. And suddenly there's an incentive for people to get them, not because they're doing good for the planet, but because it's a better option for them. And that's the kind of change that hopefully is going to improve things.
Yes, I hope you're right. Yeah, I suppose the other difficulty that comes into play with trying to change the minds of people and get the right thinking happening is social media, because there's so much scandal going through social media. And as I mentioned in the last program, we now have artificial intelligence, so you don't even know what you're looking at is real anymore. It's
this whole saying that, and I know it from a Terry Pratchett book, but like many things Terry Pratchett, he was probably referencing people before, but this whole idea that a lie can run around the world before the truth can get its boots on. It's very easy to tell a convenient lie, and people are naturally biased as humans with all the different cognitive biases we've got. There's a confirmation bias that you remember the things that fit in well with your lived experience and not the things that disagree with it. And my lived experience is that I don't change the world when I go around. I'm not fundamentally altering the world around me which I live in. So it's very easy when somebody says, we're not changing the world. Climate change can't be real, because how could you change the world? For people to really empathize with that and fit in with it. In just the same way that people who are getting vaccinated, they'll remember that their Auntie Elsa had a bad reaction to the vaccine, but they don't remember that many people who have had the vaccine and not had a reaction but didn't die from the thing they were vaccinated against because they were vaccinated. So you get that confirmation bias that feels like it supports the idea that vaccines are bad.
Yes.
When in fact they're not. And fundamentally, this is why as scientists we use statistics for all these things, lies, damned lies, statistics. We use statistics to try and avoid falling into the trap of our own biases, because we think we've seen a pattern, but statistics will give us a hint as to whether it's really there or not.
Yeah. Gosh, we could talk forever on this. It's like opening that can of worms and just letting it spill out and everybody has a go. Thank you, Peter. We're going to sort of continue on to this type of angle with a question from Paul.
G'day, Space Nuts. Paul Fiend from sunny Bris Vegas here. Quick question. If our Earth were to suddenly, or not so suddenly, become a snowball, as might have happened if our scientific theories are correct, back in our deep distant past, what effect would that have on oxygen levels in our atmosphere? Would they stay the same? Would they drop because plants don't grow really well down in Antarctica? I'd be curious to know your thoughts on this. Also, what kind of events would actually trigger that in the first place? Anyway, keep doing a great job, whoever happens to be at helm of the good ship Space Nuts. Big shout out to Heidi Campo. Wow, what a great job you did. Thank you. And Jonti, wherever you are, would love to hear from you again if Fred goes off gallivanting over to, I don't know, Norway or somewhere like that to see the Northern Lights. Cheers.
Thank you, Paul. Well, guess what? That's exactly what's happened. And Jonti is with us because of Fred's gallivanting. So, yes, you get to answer Paul's question about Snowball Earth, the effect on O2 levels, and what sort of events would trigger it.
That's great, and there's a lot to this, and it's good to hear from a local. So, yeah, thank you, and hi from...
Oh, that's right, you're just up the road.
I'm just up the road, only a couple of 100 k's inland. So, yeah, good to hear from a local. This sent me down some rabbit holes, actually. I was digging into this, and it's fascinating, because I've never actually had that thought of how Snowball Earth episodes could link to oxygen before. And it's a really, really, really good question. So I'll almost answer these kind of things in a bit of reverse order. The idea is, for those who aren't familiar with it, that at a couple of occasions in the past, one a bit more than 2 billion years ago, one 600, 500 million years ago, the Earth's climate went across a tipping point, and like the Ice Age began, but the glaciers just kept advancing, and you ended up with pretty much the entire planet clad in ice. And conditions at the equator at that point could even have been colder than we see in Antarctica right now. So really kind of dramatic conditions. And that lasted for a few million, even tens of millions of years before that condition got broken. And it makes perfect sense. Now, the climate of the Earth is relatively stable at the minute. We've just talked about our impact on it. But on geological timescales, our climate tends to sit around a fairly stable point. But what the Snowball Earth idea is reminding us of is that you have a few possible stable scenarios for the Earth's climate, of which we are one. We're one which is essentially the warm version, but equally, if you turn the Earth into a snowball, it will remain a snowball for a very long time. And the reason for that is that if you make the Earth a snowball, it becomes incredibly more reflective, and so therefore it absorbs less energy, and so it stays cold. You get this kind of feedback that keeps the Earth cold. And the idea is when you flip from one state to another, you can be locked in that new state for a very long time until something changes. Mm-hmm. Now, what could cause that? One thing that could cause that is life on our planet removing carbon dioxide from the atmosphere and weathering on the continents removing carbon dioxide from the atmosphere at a rate that cools the planet quicker than the sun getting brighter warms the planet. So the sun, when the Earth was very young, was probably about 30% dimmer, and the sun is thought to brighten by about 6 or 7% every billion years. So it's 30% brighter now than it was when the Earth formed. So the question is, if the sun was so dim when the Earth was young, how were we warm enough to have liquid water? And the answer is at that point we had a hugely rich atmosphere of greenhouse gases, things like carbon dioxide and methane, and no oxygen. And so the atmosphere was very, very rich in things that would create a really thick doona, and we were very, very pleasantly warm. Over time, the sun has got brighter, but life and weathering have removed the greenhouse gases from the atmosphere. And averaged over the entire age of the Earth, those two things have roughly balanced out. And so we still have a temperate climate now. If we had the atmosphere the Earth had when it was young, the Earth would be like Venus now. The oceans would have boiled and we wouldn't be having this conversation.
Yeah.
But the climate has kind of fortunately stayed for most of its time in the kind of warm, stable version. But there have been these two big occasions that have had this Snowball Earth scenario. Now, there's some debate over exactly what triggered that, and it's likely there were a few things. There was life and increased weathering pulling carbon dioxide out of the atmosphere, so you weaken the greenhouse effect and cool the planet down. That is most likely. You also have a scenario, incidentally, where if you make the Earth more reflective around the equator, you lower the amount of heat that's absorbed by the Earth, increase the amount reflected, and you cool the Earth as well. So one of the scenarios that's proposed to explain how we got into the Snowball Earth periods at first was that you got a period where you got one of these supercontinents where all the continental material on the Earth kind of smushed together, like we had with Pangaea, like was proposed with Pangaea. A previous episode of that, where you have most of the Earth's continents around the Earth's equator. Continental material, rock and vegetation and everything else is more reflective than water. And in fact, most of the energy coming into the Earth these days is absorbed by the water. The water is the main thing that locks in the heat and keeps us warm. And that, of course, is why Brisbane gets so warm and humid in the summers. It's why Western Europe is so pleasant in the winters compared to the middle of Canada. The water carries a lot of heat, holds onto it for a long, long time. So you have this speculative scenario where all the continents end up smushed up and near the Earth's equator. So the Earth's albedo gets more reflective, a higher albedo. So the Earth would naturally cool because it's absorbing less heat and reflecting more. Added to which, if you put the continents nearer the equator, you're in a location which gets much higher rainfall and much higher weather levels because the water at that latitude is hotter, so evaporates more, the atmosphere can hold more water. So you get more weathering, which drives more chemistry, which also acts to pull more carbon dioxide out of the atmosphere. And that exacerbates this and, removes the greenhouse effect as well. So you've got more energy being reflected and less absorbed, so the Earth cools. More carbon dioxide pulled out of the atmosphere, so the greenhouse effect weakens, so the Earth cools. That then causes the Earth to start entering ice ages where the water near the poles freezes and the ice expands towards the equator. That ice is more reflective than the water that it sits on is, So less energy is absorbed and more is reflected, and so the Earth cools. And so you get this feedback effect where the ice gradually reaches down towards the equator. And once you're in that scenario, you're in a position where even if you put all the carbon dioxide back in the atmosphere, the Earth is so reflective that it will stay cold. You're locked into this other stable state.
Yeah.
However, longer term, what happens is that you've got that ice sheet now sat over all of the rocks. So you prevent the weathering that was removing carbon dioxide from the atmosphere. You turn that off. You've still got things putting carbon dioxide back in the atmosphere. You've still got volcanoes erupting and all the sources of gases that were putting it back into the atmosphere and eventually return the weather material, weathered gases into the atmosphere. So you're in the Snowball Earth setup, but gradually over time, then your greenhouse gas levels rise and rise and rise until eventually you start to melt the ice and you get this other tipping point where suddenly you're warm enough for the ice to melt and retreat, which means you expose more water. More water is exposed, which means more area to absorb the heat, which means the Earth will warm up more, which means more ice melts, and you go back to being this kind of warmer Earth. That brings with it, though, a time when you've had the continents crunched up under ice sheets, broken up into kind of gravelly small bits of debris, and then when you start raining on that again, you get a huge amount of weathering, washing out minerals and putting it into the ocean. And that means that suddenly all that life that has been starved through the Snowball Earth epoch is suddenly going, hey, look, the Earth's nice and warm. It's a nice place to live again. Brilliant. And oh, look, there's suddenly all this food in the oceans. And so the papers that I came across when I was looking into this as a result of Paul's question, it seems that after both of the big Snowball Earth eras, there was a massive oxygenation event on Earth. So after the first one, you went from effectively no oxygen in Earth's atmosphere to Earth's atmosphere being about 2% oxygen, which is a big jump from nothing to 2%. And then 500 million years ago, you had the end of the most recent Snowball Earth thing, and you got another mass oxygenation event where suddenly you've got all this nutrient and all this stuff washing off into the oceans, prime conditions for things to grow, and a huge amount of oxygen released. And that is thought to have been what drove oxygen up to something comparable to its current levels relatively quickly. And that then led to there being sufficient free evidence for what's called, I think, the Cambrian explosion, where suddenly you've got an Earth that has all these different niches suddenly freed up, and the source of ready oxygen, and everything goes crazy, evolving to fill the available opportunities. And so all of that kind of gives you an idea how we think Snowball Earth episodes could happen, and what would happen to oxygen afterwards, which seems to be the accepted scientific wisdom that after a Snowball Earth episode, when it ends, you can get the oxygen suddenly getting significantly more oxygen-rich as life takes advantage of the new conditions. What would happen to oxygen now that there's a lot of it in the atmosphere during the Snowball Earth period? I couldn't find any speculation on. Wow. So it's a really interesting question. Now, it doesn't mean there's no speculation out there. It just means that I couldn't find any. There's big difference there. But there's a few things that are going on that I think could be interesting. Firstly, there's a huge amount of oxygen in the atmosphere. So even if you stop producing it and you manage to keep alive the things that use it, it will probably go down very slowly just because there's so much of it. And if you were killing off a lot of life, then, to be honest, there's not as much using it anyway. Volcanoes erupting carbon dioxide and particularly methane that's been erupted and outgassed, particularly towards the end of the Ice Age kind of period. Getting lots of methane released into the atmosphere would remove the oxygen as the methane and the oxygen interact with each other. And if that was happening quicker than life was putting new oxygen into the atmosphere, then you can imagine that leading to a bit of a dip in the amount of oxygen in the atmosphere at the time. But my guess would be that probably during the Snowball Earth period, the oxygen levels wouldn't change all that much. You might be producing less oxygen, but you'd also be using less. So that will balance out. But what you would get over time is, particularly if you killed off a lot of life, you get this slow, steady increase in greenhouse gas levels because you're still pumping out the same amount in terms of volcanism, but you've removed the weathering that's taking it away again. And so that would lead to the greenhouse gas level rising slowly over time until it got to the point where it turned it back over the tipping point and allowed the Earth to warm up again. And that would probably then be a very bad thing because the sun is now much more luminous than it ever has been in the past. Yeah. And so if you get a runaway greenhouse effect now, that's a lot more problematic than it was 500 million years ago. And maybe that could lead to conditions where you don't hit our current stable level, but you go past that and you end up hurrying the end of the Earth as a habitable world, effectively.
Oh, fun. Yeah.
Cheerful thought.
I just did I'll get some negative press for this, but I just did put a question into ChatGPT. Would current oxygen levels on Earth reduce if Earth were to freeze over? And it's come up with a few scenarios, but basically says it says most oxygen on Earth comes from photosynthetic organisms, mainly marine plankton and land plants. If Earth froze over, ocean surfaces would be sealed under thick ice, preventing sunlight from reaching most marine photosynthesizers. Land plants would die or go dormant due to cold or lack of liquid water, so oxygen production would drop dramatically.
Yeah. And that makes sense, but I'd argue that oxygen use would drop dramatically as well because you kill the things that are using the oxygen.
Yes.
The other thing that I stumbled across in my reading, actually, and that just reminded me of, was one of the things that tied into this idea of the Snowball Earth stuff was how on earth did life make it through? And one of the things that people's modelling found was that even though you'd get ice all the way down to the equator, the processes that happen at the equator will probably prevent that ice being more than about 10 meters thick. And studies have shown that enough light can make it through ice for photosynthesis to continue, unless that ice is 20 meters thick or more. And so there'd likely be a band where you could continue photosynthesis under the ice because the ice is not thick enough to block all the sunlight. That seemed to be the argument. There was some discussions of where the pockets of life holding on through the hellish times would be. And that was quite interesting, but like I say, I'm not a biologist, so that is straining my expertise to look at exactly how life would adapt to those conditions.
Indeed. All right, Paul, thanks for the question. Great one, and there might be more to talk about that in regard to that down the track. This is Space Nuts with Andrew Dunkley and Jonti Horner.
3, 2, 1.
Space Nuts.
Now, Jonti, a couple of questions have come in about objects or events that have happened in space. Casey has messaged us. Hello again. This is Casey from Colorado. I recently read a little bit about the record-breaking KM M3230213A. Please correct me if I'm wrong, but detecting a 220 peta-electron volt neutrino is pretty crazy considering that that's like 30 times more energetic than the previous record holder. What could possibly be its source? Love the podcast and hope you're both well. Thanks from Casey in Colorado, and she hopes you're well too, Jonti.
Yes.
Then again, she might be talking about Fred and Heidi. I don't know.
So this is a really interesting one. I must say that I hadn't seen this announcement, and so this was a really interesting thing to read about. This is a neutrino that, according to the name, was seen in 2023 on February the 13th. And it was detected by this huge array of detectors on the bottom of the Mediterranean Ocean, Mediterranean Sea, about 3.5 kilometers below sea level, in the pitch black of the deep ocean, where they have all these detectors that have the job of detecting incredibly faint flashes of light that occur when cosmic rays or neutrinos collide with an atom in the ocean and cause a cascade of light as there's this whole collision chain of particles being formed and energy being released as the energy from those things is dumped into the ocean. And this occurred before they'd finished building and testing this array, so it was during the testing phase. And it is, reliably says on all of these websites, by far the most energetic neutrino ever detected. And it is so energetic that there is no source within our galaxy that could generate a neutrino that energetic that we know of.
Wow.
And if it had been generated by something nearby, we'd have seen other things happening. You might have seen a very powerful gamma ray burst or something like that. And no counterpart was detected. There was nothing that happened at this time that synced up with when this happened. Now, should be said that when I searched for this, there's a nice little article describing it by the Astrobytes website, which is a website run by graduate students in astrophysics in the US that tries to be a literature review journal club for other graduate students and to give students an opportunity to practice science writing about things out of their field. And there's a bit of a description of it there. And that's a nice little website if you're interested in getting a little snapshot summary of research papers. They try and do one a day. But I also stumbled across the official page for this event, which is published by the network that are running these detectors. And that's got a lovely little YouTube video right at the top that you can watch. It's about 2.5 minutes long that describes this thing, how it's detected, and some of the possible suggestions for its formation. Now, going beyond that to what could have created it is really pushing beyond the bounds of my knowledge and expertise. So I'm afraid, Casey, you're going to have to accept a journeyman's explanation based on what I was able to read around about this, which digs into things that I honestly don't fully understand. But the argument is because of the incredibly high energy of this thing, it couldn't have been generated locally. And that points to an origin in the very distant and therefore very early universe. Now, there's some theories that fall under the branch of what I think is called quantum field theory that talk about there being photon fields permeating space. And I don't fully understand what that is and what that means, in all honesty. But the idea seems to be here that you've got radiation from the cosmic microwave background or from very early in the universe that includes incredibly high energy radiation at that time, because that's a heat from the Big Bang. Now, nowadays, we see that as a cosmic microwave background. It's very low energy levels because it's been redshifted. But at the time, the energy levels were incredibly, incredibly high. And that means that these photon fields, if you follow the quantum field theory ideas, were incredibly intense. Now, one of the ways that you can produce neutrinos that is predicted by this predicts what are called cosmogenic neutrinos. Now, it should be said that none of these have ever been detected until potentially this one, but it's one of the predictions that quantum field theory makes, is that you should see these cosmogenic neutrinos that are generated by cosmic radiation rather than a specific event like a gamma ray burst or a supernova or something like that. And the idea is that in the very early universe, you've got these incredibly high amounts of energy, and that means that these photon fields, I think they're called, can interact with particles of matter. And when you get this interaction, that can lead to the production of an incredibly high energy neutrino. Now, the very high energy neutrino, as we know, neutrinos are about the weakest interacting things we know of. So once you produce a very high energy neutrino, that can pass across the entire universe without interacting with anything. We've got millions of these things passing through our bodies as we speak, and we just don't feel them, which incidentally is why to detect them, you want to be at the bottom of the ocean or in a huge volume of water, so that you maximize the number of atoms available for one of these to by chance collide with and give you the light show, because you need a huge volume of water to get even one neutrino to hit something and give you a show, because they're that weakly interacting.
Yeah.
Once you produce these cosmogenic neutrinos, they then carry on through the universe forevermore at ridiculously high energies. Now, the bit I quite honestly don't understand with this, and none of the things I've read have been able to explain to me, is the fact that if this thing was created with the cosmic microwave background, I would have thought it should be redshifted by the expansion of the universe in the same way that photons are, the light we see it. And doing a bit of reading around, it does seem that neutrinos can be gravitationally redshifted. So if you get a neutrino produced at the surface of a neutron star that is one energy, by the time it escapes from the neutron star's gravity, it's lost energy and it's effectively redshifted. What I haven't been able to find out, though, is whether the expansion of the universe would redshift neutrinos and therefore lower their energy. Now, if the expansion of the universe doesn't lower the energies, then this makes perfect sense. You know, you've got this incredibly high energy neutrino that's tied to how high the energies were when the universe was young, and it's only just reached us now. If they are redshifted, then that makes this even more head-scratchingly awesome, because if it has been redshifted and its energy dropped by an incredible amount and it's still 220 peta-electron volts, what was its energy when it was formed? And I just don't fully understand that. So my knowledge is limited of this. I've done my best to read around it and get an understanding of what they think is going on. But I guess what comes out of this for me, it's just a very cool detection. But if you want to push the boundaries of what we know and build theories of how the universe works, our theories will eventually go beyond our level to observe the things that they predict. A good example of this I always go back to, because it's my own wheelhouse, is Newton's theories of gravitation, which he published in Principia Mathematica in 1680, 1682, around then. And that gave us mathematical tools that allowed us to work how things moved in gravitational fields, allowed us to work out orbits and predict things in the future. And that's been incredibly powerful. By the 1800s, observations were starting to show that the orbit of Mercury was behaving slightly different to how Newton's gravitation would predict it would work. That effectively led to the precession of Mercury's orbit, the wobble of the orbit, wobbling at a slightly different rate. And nobody could explain that. It led to people speculating that maybe there's an unseen planet closer to the sun than Mercury, because it would seem for the planet Uranus that an unseen planet pulling it around could change its orbit, and that was Neptune. But that didn't work. We never found anything. And it wasn't until Einstein came up with the general theory of relativity that, as a byproduct of that, his method for understanding how gravity works accurately models the precession of Mercury's orbit with incredible precision. So when Newton came up with his ideas, the predictions you would make with Newton's gravity were so accurate that it was only 150 years or so before our observations got good enough to show that Newton's theories were wrong. They disproved those theories, but we still use them because they are so accurate. They're slightly off, but they're so accurate and easy to use that they're easier for me to use in my modeling than general relativity, when the uncertainties in the things I model are so great that the difference between those two is lost in the noise. So it's just easier for me to use Newton's laws. But it's a really good example of how theory makes predictions that are verified for a very long time, but eventually you get to the point where you go beyond what theory explains, and that leads to new theories. And in this case, it's a case where there are these set of theories that are very much at the cutting edge of science, where the predictions that they make are predictions of things we have not yet seen, because it's fairly pointless to only predict the things we have seen and not go beyond that. So they predict things we haven't yet seen. One of those things is the existence of cosmogenic neutrinos, and it may well be that this is the first detection of a cosmogenic neutrino, which then adds credence to the idea that these quantum field theories work and make sense. So it's that interplay between theory and observation and experiment that I think is really interesting, even if, to be honest, I really don't understand it.
And what Jonti is saying, Casey, is that it'll be 150 years before someone comes up with a model that actually explains it. Possibly. It could happen that way. You never know. And thanks for the question, Casey. And I assumed female, but looking at the spelling of Casey, could be male. Apologies if I got that the wrong way around.
Roger, you're allowed to clear here also.
Space Nuts.
Our final question today comes from young Henrik.
Hello, it's Henrik from Portugal again. This time I'd like to ask about the object MWC349A. What makes it so extreme? How does it emit lasers and masers? Can you explain to my dad what masers are? Thank you, bye.
Thank you, Henrik. Yes, MWC349A. A for apple, not 8. That's what I thought he said. But this is a mysterious emission line star and radio bright object in the constellation of Cygnus.
Yes,
and it's suffered an intensive mass loss.
Yeah. It's a really interesting object. Now, I wasn't familiar with this object before the question came in, and it's probably something that when I was Henrik's age, I'd have heard of and come across and would have really found fascinating, just like Henrik does. It's a fabulous question. As best we understand it, this is something that is a very luminous, very bright star, much younger than the sun. It's probably at most 5 million years old, but it could either be a baby star that's still forming or a very massive star that's just coming to the end of its life, even though it's only 5 million years old. And there's been a lot of debate of that over the years. It is famous and it's prominent because it's one of the most bright things in the sky at millimeter and radio wavelengths. It's very, very bright, very obviously visible, even though it's way too faint to see with the naked eye. Part of the reason it's too faint to see with the naked eye, though, is that there's a lot of dust and gas around both where the object is. We found that it's got a disk of dust and gas around it that's edge onto us and is blocking some of the light. Plus, it's in the spiral arm of the Milky Way, so there's a lot of dust and gas between us. So this thing has an apparent magnitude of about 13, but there are about 10 magnitudes of extinction along the line of sight between us and it, which means that for every 10,000 photons it emits, only one reaches us. In other words, if you could clear all the dust and gas out, this would be a third magnitude star and easy to see with the naked eye.
Right.
So that's intrinsically how luminous it is. It's thought to be about 1,300 parsecs away, so that's 3,900, 4,000 light years. So the light we receive from it, we're seeing it how it was 4,000 years ago when that light was emitted. And because it's so luminous in radio wavelengths, it's been fairly well studied. And in particular, it gives off a lot of energy at wavelengths linked to molecular hydrogen. And it's known as one of the few hydrogen masers that we see in the sky, which leads to Henrik's question about what is a maser. The very simple answer to that, which doesn't tell you anything, is that a maser is a laser, but happening at millimeter wavelengths, so in the infrared or radio. But it's the same physical process. And in fact, masers were what we developed before we could do lasers, because lasers are the same phenomenon happening at visible wavelengths in the optical. That is a very accurate description that tells you actually nothing about what's going on. And I dug into this a bit because, like a lot of people, I use lasers and think about them, but never really remind myself how they work. Laser stands for light activated stimulated emission of radiation. Sorry, light amplification by stimulated emission of radiation. It's an acronym. And maser stands for microwave amplification by stimulated emission of radiation. So it's the same process, just happening at longer wavelengths. What's happening effectively is that when atoms are excited, when energy is pumped into atoms, and that energy is absorbed by them, it makes the electrons in those atoms jump from one level to a higher energy level. And they are very specific jumps in energy. It can only jump by a certain amount. It can't miss a gap. It's got to get exactly the right jump to jump from one level to the next. So those energy levels are very specific wavelengths, and we actually calculate them at university as part of our undergrad quantum mechanics courses and things like this. It's one of the tasks you have is work out the energy levels of a hydrogen atom. And they are quantized such that when you're at an energy level, if you want to jump down to another one, you can only do that by emitting a single photon. You can't emit multiple photons that add up to that level. You can only emit one photon, and you have to hit the right energy level to get the gap. And so that's why excited hydrogen glows at very specific colors. So the photo behind me, which won't be visible if you're listening to this as a podcast, but the photo behind me shows the Helix Nebula, which is a the Trifid Nebula, which is a star-forming region. And the middle of it's a very distinctive pink color. And that pink color is hydrogen alpha emission, which is hydrogen atoms jumping from the third energy level to the second, emitting light, and all emitting light of exactly the same color. So that's known as spontaneous emission. That's where the atom sheds its energy by emitting light of a certain color. Stimulated emission is where something happens to trigger that emission specifically at a specific time. So you've got an atom that is excited, is sat at a higher energy level, and something gives it a nudge and causes it to emit energy. And the way that works is that it absorbs a photon of the same energy, of the energy level difference that it was going to emit anyway, and then immediately emits 2 photons of that energy. So you get 1 photon in and 2 photons out. 2 photons out can hit 2 atoms and trigger them to emit, which means you get 4 photons out and so on. So you can get this cascade. So what makes it work is that there are many ways of exciting the atoms in the first place. They don't have to just absorb photons. They can be excited through magnetic fields or all sorts of different things going on. And so a maser is effectively somewhere where emission is being stimulated by incoming photons of a given wavelength, which results in more photons being emitted of that wavelength than are coming in. And so you get this amplification effect. So in this case, this being a hydrogen maser means that you've got a lot of hydrogen gas there. That hydrogen gas is being irradiated by emission of a specific wavelength by this object, and that is stimulating the emission of more photons, which means you get an extremely bright emission at that wavelength because you're getting this amplification effect. And so that's how this thing works as a maser, and that has been very useful in allowing us to study it because it means we get a stronger signal, we get more light, so there's more we can study. What my research around it this morning kind of found out was that there is some significant debate historically over whether this is, firstly, a binary star or on its own. There's another very hot blue star very close to it in the sky that for a long time was thought to be a binary companion. And that's why this is MWC349A, because there's a star MWC349B. Now, recent studies that have measured the radial velocity of the two stars suggests that the star B is moving 35 kilometers per second compared to star A. So they're not gravitationally held together anymore. So they're probably not now a binary, though there is some debate whether they were in the past, whether they were held together by gravity, and then those two stars have shed mass. As we said, this star seems to have thrown mass away in recent times, may even have lost half its mass. It may have gone from 40 solar masses to 20. That weakens its gravitational pull until eventually the binary falls apart. So that's one part of the debate, but the recent results seem to suggest that even if they were a binary in the past, they no longer are. The other debate is whether this is a very young star that's only just forming now, or whether it's a star that formed a few million years ago and is coming to the end of its life. And you'd have thought that was obvious, but for stars like this, it's quite hard to tell, especially when they're so obscured by gas and dust. Now, if it was a baby star, the really odd part of that will be, why are there no other baby stars around it? Stars kind of form in big nurseries, and particularly massive stars don't tend to form alone. They tend to form in big associations where lots of stars are forming at once. And there's one relatively near this called Cygnus OB2. And one of the suggestions for this star, if it's an older star that's coming to the end of its life, is that it formed in that association and was ejected in an encounter with other stars and flung outwards. And we're seeing it quite far away because it's travelled that distance through its lifetime. So it formed there, but it's escaped. If it's a baby star, we have the problem of how is it only just forming in an area where there's not really any other stars forming around it? Recent studies have suggested, by looking at all things, the balance between carbon-13 and carbon-12, these two different carbon isotopes, in the gas that has been shed by this star, recent measurements of that have suggested it's actually an old star, well, old for its mass, about 5 million years old, but coming to the end of its life, that has been shedding mass, and that is explained by the balance of the isotopes in the gases that it has emitted, which fits in a bit better with the idea that it may have formed in that Cygnus OB2 association a few million years ago, have been flung outwards and escaped. Would also fit a little bit with the idea that star B next to it was once held to it as a binary, but with the mass loss, they've separated and they're going their separate ways. That happens all the time. And so that all kind of as a narrative seems to fit together, but it's got a disk of material around it that's nearly edge on. It's got jets of material coming out of it. There is a suggestion that it's probably shed something like 20 times the mass of the sun over the last few 100,000 years, and that it's shedding something like 1/100,000th of a solar mass per year, which doesn't sound like a lot, but that's a huge amount of mass to be throwing away in every given year, which means it would throw away a mass equal to the mass of the sun in just 100,000 years. That's really significant mass loss going on as this star comes to the end of its life. And it's a really interesting case study of that detective story again, of how we gather clues from all these different types of observations about a star that, for us at optical wavelengths, is so heavily concealed from us that only 1 part in 10,000 of the light it emits actually reaches us. The rest of it gets absorbed en route. And that's why it's been such a challenging problem for astronomers for so many years, because it's really hard to see what's going on. But by looking at the masers emitting this light, by looking at all the different things going on around it, by doing clever studies of the chemistry of the gases around it, we can start to piece together its life story and figure out what it is. I don't think that story of discovery is finished yet by any means, and it may well be, Henrik, that when you're older you can actually work on this object and learn more about it yourself. I suspect people will still be discovering things about this object in decades to come, but it's a really fascinating object, and I'm just so delighted that you brought it to my attention, because I'd never stumbled across it before, and it's really, really cool.
Yes, it's sorry for this. It's amazing. But Henrik, thanks for the question, and you do sound very astute, and maybe you will be the one that will solve it in years to come. Lovely to hear from you. And if you have questions for us, please send them through. We can take your questions on our website, spacenutspodcast.com, spacenuts.io. Click on that little AMA link up the top, and you can send us text or audio questions, or both. Some people have done that. And don't forget to tell us who you are and where you're from. And we're kind of running sort of parallel with the number of questions we need each week. So we haven't got a big stockpile at the moment. So it's a good time to send some questions into us. So please do. Would love to hear from you. Don't even worry if you think it's dumb, because there's no dumb questions in astronomy and space science. There's weird questions, but there aren't any dumb questions. And while you're on our website, have a look around. There's a little link SHOP link. It's really good. You can get some Space Nuts memorabilia there, or sign up to our Astronomy Daily news feed. And if you are interested in becoming a patron, you can do that via the website as well under the Support Our Podcast link. Those are just options. None of it's mandatory, and we appreciate all the support we get. So thank you. And Jonti, thank you so much. It's been great to talk to you, and we'll see you on the next episode.
Yeah, thank you for having me. It's good to be back.
Always a pleasure. Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. And thanks to Hugh in the studio, who couldn't be with us today because they're going to hate me for this one. He got lost in a mazer. Oh, dear. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.